Um, can you see the slides?
Yes, I can.
So thank you very much, Satyajit sir, for your nice discussion. So now we are going to go to the approximate. Okay, wait. Can you
I can see your screen. Yes.
Okay. So now let us talk about neural network. So what's neural network? Most of you at least heard about a neural network in your daily life. So neural network is a computational learning system. So it uses a lots of data and then gives you a desired output in another form. So the concept of neural network, as you can see, it comes from neuron. So like our brain, it functions, the neural network works like our brain. So it is inspired by human biology. So neural network is just one of the tools of machine learning. And if we go to the next part, that we can see that there are lots of real life applications of neural network in our daily life. And in mechanics and modeling, as Sir said, there are lots of neural network application. So so if we go to the next slide, so let us talk about how neural network works. So this is strain. It is our input, and with this strain, the material will have some stress. So this stress-strain relationship is different for different materials, but this stress-strain relationship is dependent on the constitutive equation. So how does value of stress will be, what the value of stress will be is strictly dependent on the value of strain, and different model will give you different value of stresses. So what neural network will do is it will approximate the value of stress. So in our present case today, we will see the strain as our input or the loading as our input, and the output will be stress. And the neural network will model, will approximate the value of stress when we give it some value of strain. So there are some terminology, and it's not important that you know every bit of it, but just bear with me. So we can at least think of neural network as an organism. Every organism have different parts. So let me introduce some parts of neural network. So neuron is different. It can think of a biological neuron. So input layer, this is important. So input layer is this part of the neural network, this part of this organism, if you say so. So it takes the input. Its job is to receive the input. Now there is an output layer which will give you output. So these two, this is input layer, this is output layer. So input layer will take strain, and the output layer will give out stress. And there is a hidden layer, which is actually the main part of our neural network. So you can it can be a hidden layer, can be part of a long, it can be a very dense long network, but hidden layer, actually this is where the approximation happens. So now there are activation functions we will discuss later, and weights and biases. Now let us go to the next part. So as we can see, this is the value of strain, and when does and this is input layer, and A is the value of each neuron. So these circles, as you see, these circles, it has some values. These circles have some values, and these values are the values of neuron. So A, we will term it as neuron values. And if we go to the next slide, we will see weights. and this is very important. So what weight does, it changes, it is like, if you can think it as some kind of parameter. So when we give stress in the input layer, weights modifies this input and changes it so much that in the output layer it becomes the value of stress. So you can think this whole thing as a function. So the value of A changes, the value of weight changes, and the value of weight changes in such way, the value of weight will be in such way that the output will be our stress. So now there is a bias term. You can think of bias term as an additional term. If I do it correctly, if you see that, like a bias term is an additional term, and weight is an multiplication term. This is the simplest way you can define weights and biases. So what weights does, it multiplies with this A, and what bias does, it adds to this way A. So, and in that case, this value will be completely different than this. And then when it goes again through this neural network, this value will completely change, and finally we will get stress. So it works as a function. And now we will go to the next slide. So now if you can see, so this is the final form. So this is weight. This is the neuron of previous layer, and this is the bias. But the whole thing will be inside a function, and this function is called activation function. So in every line, in every line from this point to this neuron to this neuron, the value will change, and this will change according to this particular function, which is activation function. So and the activation function can be different types of function. As we can see, we use multiple types of activation functions: sigmoid function, hyperbolic function, ReLU function. In most cases, in elementary usage, we use kind of sigmoid function, but there are lots of functions. And these functions are kind of special functions. So you cannot just use any function. You cannot use just sine or cos or that type of function. These functions are quite general functions, and we use it to give us proper neural networks. So now let us give an example. So what neural network, here F is the activation function. So if we look at it, that the value of A1 and L is equal to 3. So this output value is predicted output value. And so in neural network, this is the input. It goes to these neurons, and while it goes through the neurons, it gets multiplied by weight. It gets added with bias, and then it goes through an activation function. And finally, we get another completely different number, which is our output. So our goal here, so now initially, the output value will not predict properly, definitely not. But we know the output data from our simulations or our numerical results or our experiments. So we will compare, and there will be an error, and we will then try to minimize the error. And at some point, the error will be negligible. So there are a number of ways to minimize these errors. So one is gradient descent method. So this is very important. I think the terminology part, the activation part, it's fine, but this is very important. You have to understand this. So as we can see, our output is dependent on two things. It is weight and it is bias. So the error, the cost function, what we call, the error will error will be measured like this. This is the experimental value or the actual values, and these will be the output of neural network in a simple way. So our error or our cost function C is dependent on two things, W and B. So if we change the value of W, the cost function can either go big or can either go small. And our target is to make this small as possible. We want to minimize this cost function. We want to minimize the difference between our original value and our predicted value. So we want to change this value of W. We want to change this value of B in such way that the cost function minimizes. So what we do, let's see for the case of W. So, and from this figure, we can see that the value of W is dependent on, the cost of function is dependent on the value of W. So this is the point, initial point. This is the initial value of W. And in gradient descent method, now think of it. We can increase the value of W. If we increase the value of W, what will happen? The cost function will increase. That we do not want. And if we decrease the value of W, the cost function decreases. So how the neural network will understand this? So we will gradient, we will take the gradient. So when we take the gradient of the cost function with respect to W, it will be negative, definitely. And by negative, we can say that the value of weight must be reduced. So let's further explain it. So this works like steps. So there are two things. Let me do it like this. So this is my initial value of weight, and these are two terms. I will explain it now. So this is called learning rate, and this is called the gradient. So if the gradient value is negative, the weight will be positive, and if the gradient value is positive, the weight will be negative. So this is the step, and this is the value of this. This signifies in which direction we will go. So the gradient will decide which direction the weight will go, and alpha will decide how much step we will go. So if the value of alpha, or the learning rate as we call, if it's too big, then if the step is too big, then the value will overshoot. We will go from this point to this point, and from this point to this point. We will not reach the minimum quite well. But if the value of learning rate, alpha, is very small, then in small step, we will go to the minimum point. So let's further go. So here, the higher the learning rate, the possibility of overshooting is very much. But when the learning rate value is very low, even the time will take, the time taken for performing the neural network operation will be high, but the value of the accuracy will be very good. So cost function. So as we can say, as I've said, the cost function determines how good the neural network predicts. So I want to minimize it. So now if we summarize the steps of the gradient descent algorithm, we will, there are two parameters, W and B. I have shown the gradient descent application for W. You can do the same for B. So since we need to consider the impact of each one, so our final prediction will be partial derivative. So I think many of you do not know partial derivatives or even calculus. So we will not go into that much detail, but think of it like that. The value of W and the value of B will change according to this gradient descent algorithm in such a way that the value of cost function will get minimized. So and then we will solve it. So let's have a simple backpropagation method. So in our example, the bias will be 0, so no additional term, and the activation function will be a linear function. This is as simple as it can be. So and the error function will be this, the mean squared error, and then we will go to the next part. And as we can see that the final output layer is something like this, and see the final output depends on each and every weight values. and all the neuron values. So now we want to find this the W value. So the error will be minimized in gradient descent algorithm in such a way that the error value will be very low, and this del W means how much change we will do. As you can see, this is the alpha, this is the gradient. The gradient will decide which direction we will go, and alpha is the length of the step. So if you partially differentiate this, we will get these values. We will come to this later. So now let's think about a simple backpropagation problem. This is a simple neural network. My strain value is 0.1, and my experimentally or numerically, I have found that the stress value is 20 when the strain value is 0.1. Now, and this is the initial weights. These are just normal. These are not actual weights. These are just initially I have set the value of this weight is 5, 10, 20, 10, 4, 4. These are random. Now, from this point, the strain, it will be multiplied with weight, and then it will become this 0.5. Again, this will multiply with 10, the weight, and become this neuron. Weight, neuron. So I have got 3 different values of neurons. And then again, this value will be multiplied by the weight, and then it will go to the output. Weight, output, weight, output. And I will finally get the value of stress 17, which is not actually correct. My value should be 20. So what I will have to do is to change the value of these weights in such a way that the output value becomes 20. So now let's see what we can do. So these are the del W is the increment. From the gradient descent method, we can calculate how much this value of weight will change. So this is alpha step. Delta means the difference between the output and the predicted value, actual output and a predicted value, and A is the value of neuron. And I got that the W11 is 0.15. And similarly, by gradient descent method, I can calculate all the other values of all the other increments of W and weight. So if you see that, if we go back, if you see that these are the value, these are the changes, increments that I need to add to the weights. So 0.15 I will add to this, 0.3 I will add to this, and 0.6 I will add to this. And then I will get a completely different new sets of weights. And similarly, using gradient descent method, I can change these values too. And if you see, finally, what happens, now the weight value changes. Now we have new sets of weight. Now the strain is still 0.1. It will get multiplied with the weight, new weight, and becomes 0.53, 1.012, 2.012. And these will be multiplied with these new sets of weights. And finally, I get 18.98. Previously, it was 17. But by changing the values of weights, I have gotten a more accurate results. And this is just one iteration. If we do 10 or 20 iterations, the value of the output will become 20. So my neural network will easily predict the stress strain output accurately. So, so this is how backpropagation algorithm works. So what backpropagation algorithms does is that it goes, it's like a reverse action. Like I gave stress, I gave strain, my neural network gave me an output. But the difference between the output, by calculating the difference between this output and actual output, I changed the value of weights, and finally, then again run the neural network and got a different output. And in this way, we can get a proper neural network function. So now if we go to the next slide. So today we will do some hands-on hands-on work. So our system is something like this. This is a composite material with matrix and fillers. And then what we're going to do, we have conducted a number of numerical analysis, stress strain analysis. And then we got these stress strain curves. These are our data. And our input data will be the percentage of filler volume. So as this is a composite material, the percentage of filler material will change how the stress strain curve looks. So filler material fraction will be our input. Our strains will be input. 3 strains, different strains will be our input. And our target is the stresses, the 3 different stresses. So our input range will be from 1 to 15. Our strain range will be 0 to 0.0, 0 to 0.02. And our data points will be 750. So what we did 750 numerical simulations, and our training set will consist of 765 data points, and our validation set will be 75. So what we're going to do, we are going to use these available data to make a neural network model that will properly predict any type of composite this system. So I have 1 to 15, but if I want to see the stress strain curve of 14.3%, then what we're going to do, we're going to use this neural network. So finally, in our hands-on work today, Thakur will introduce some coding. So I will like to ask Thakur to carry on the presentation.
Thank you so much, Shajedul sir and Mahmudul, for your great descriptions of our work, of what we are studying.
So Shajedul, before you start the hands-on session, I'd like to see if there is any question from the audience. So one thing I'd like to make sure, so you already have the data set, I guess, from the Excel sheet. So what we did here, we choose 15 different volume fractions. So your volume fraction is basically the area of these blue dots divided by total area. So we have 15 different volume fractions varying from 1 to 15. So you can see 15 different stress strain curve here. And we vary the strain value from 0 to 0.02. So for our input, we have 4 different input parameters, which is filler volume fraction. And when we apply load in x direction, you will also have some strain component in other directions. So this is epsilon xx, yy, xy. So this is a 2D problem. So you have these 4 different input parameters, and you have 3 different target parameters, which is basically 3 different stress components. So the total data point here we mentioned is basically we took 50 data point between this 0 to 0.02. So you can see this graph here, but this is basically consists of 50 different data points. So that's how we get total 750 data point in your Excel sheet if you open it. And from there, we choose randomly 675 for the training and 75 for the validation. And then based on that, if you go to the next slide, in the next slide, we have some result, how it looks like, and then you will do it in your hand. So you can see these are our input. We have 4 different input parameters, and we have 3 different output parameters. And then you can see my neural network prediction versus original data. So there is one question, how we are getting this value from 1 to 15. So can you go back to the previous slide? I can explain it a little bit more. Mahmudul, can you go to, yeah, thank you. So if you see this blue dot, right, these blue dots there. So say, for example, this is total 100 by 100 mesh, right? And among this 100 by 100 mesh, there are certain portion is occupied by these blue dots. So if you calculate the area of these blue dots and divide it by total area, then it will be a certain volume fraction, right? So for example, say this is 15%. Now you want to reduce it. So basically you can exclude some of them from your domain. and that may give you 12%, right? So that's how we actually varied it from 1 to 15%. Okay. So this is just an artificial case that we generated, but in real scenario, you will have this data from the experiment or from somewhere else. Now you can understand, like, this is a very simple case, and the way we generated the data using some J2 plasticity model. But in real scenario, there are many interesting concepts. For example, say if you work with nanocomposite, you will see after a certain volume fraction, the stress and behavior might be different. So you can see there are some agglomeration of this particle, and it will cause the damage of this material. So if you even you increase the volume fraction, the strength of the material will not go. So for this case, this is a very simple case. I mean, we have generated it numerically, and this is simple following the J2 plasticity law. But in real scenario, that is very different, and that's why we need this kind of machine learning model to explain or predict those kind of materials model. So with that, I hand it over to Shajedul. Thank you for your question.
Thank you, sir. So I want to just start with something as basic as, so first thing we need to do is go to Google search, Google Colab, go to this link, come here and click upload right here. Choose the file that I just sent and in the chat, or also I provided a box link, and then upload that file. Once you upload that file, we should have something that looks like this. So I think everyone's with me so far. So
allow them some time. Allow them some time. So after you do that, I mean, those who are following, you can raise your hand or put in the chat that you are able to do that.
So just to repeat, search Google Colab, go to this first link that should take you here, and click here, upload. And once you click upload, then that'll be it. Choose that file.
So after, you can see there is a folder button at the left. So if you click that part, you will be able to see your files there. So I am asking about this one. No, not this one. Can you go back? Go cancel. So if you've done it correctly, so if you click this folder button here, I'm not sure if you can see it. Yeah.
Oh, sir, the file won't be here. The file will actually be here. So I'm using it.
You haven't.
Can
I see. You
directly
give the. Okay.
Yeah.
You have to upload it at every session you run the collab. Every session you restart the collab, you have to upload it.
Yeah. So actually, we're not using any local file. Just the notebook will be enough. I've given the notebook to simplify the process.
Okay, I understand. So you basically gave the link. That's yes. Okay. But I would like to mention one thing here. So we are using Colab so that everyone can follow, because if you install different version of Python and different version of your TensorFlow, that may have some issues. So Colab is a common platform for all of us. So that's why we preferred Colab, but it is recommended that you install this machine learning modules in your own computer and try this later on. So right now we are going to use Colab. Thank you. Continue, Shajedul.
Okay. So the first section of code that we see here are we are just importing some libraries that we will be using later on. I'm not going to go into explaining all these libraries, but I think anyone familiar with Python is familiar with these libraries. So the next step is we're reading the data set. Now here I am reading a data set from GitHub, which is this data set right here. As you can see, the data has 1, 2, 3, 4, 5, 6 columns. And these is columns of data set. We are labeling them as percentage, as using this command. Percentage, strain in the XX direction, the normal strain strain XY, strain YZ, and so on, as Mahmudul has already showed in the presentation.
I would like to mention one thing here. There is a correction. So this would be strain YY, and this would be strain XY. So we did 2D problem, and we have component like XX, YY, XY, and this is also XX, YY, XY. We don't have any Z component.
It was a typing error. Thank you, sir, for the correction.
Yes.
So
Yeah.
I'm going to keep the names like this, just so it doesn't cause any problems in the following code. But of course, you can change it later on. So afterwards, what we see is you can actually ignore this. But what all of this is ultimately doing is we are plotting the stress strain graph that we already saw, just to look at our input data. So we have for 15 percentages from 1 through 15, we have these 15 stress strain graphs, and we will try to train a neural network to try to fit these curves for each percentage. Now, the first step is to split our data into X and Y, X being the input features and Y being the output features. So in our case, the first 4 columns, percentage, strain, and the 3 strains, are our input features, and the Y dataset are our stress values. So we are trying to predict the stress values by using the strain values and the percentage of volume fraction. Next, we need to do some pre-processing of the dataset. By pre-processing, we mean that a dataset needs to be normalized. Normalization has not been talked about, but just to give you a very slight brief, if your dataset is something like 1, 2, 3 in X, and maybe in Y there is 50, 60, and in Z there is 10 to the power 8, then that will cause some very big problems for the neural network. So what we do is we bring them all in the range of 0 to 1. And for that, we are using something that's called a min-max scaler. So it uses the minimum value and the maximum value of the dataset to scale the dataset to 0 to 1. So we are using this min-max value. So as we will see, if I go back here, so here we can see that the strain values are way different magnitudes in different cases, and also the percentage is different magnitude. But once we take them all 0 to 1, they will be easier. It will be easier to train the neural network. So for that, we use a min-max scaler. So as you can see, first we fit the X data, that is the input features, into a scaler, and then we use that to transform the X data into scaled X data. Next, we apply the same transformation to Y, but this time fitting it for the Y data, and then we apply the scalar transformation. Now that once we have the scaled X and Y data, we want to split them into 2 parts, the test data and the train data. Now, to keep it simple, we are keeping a test size of only 0.01, like 1%, and the train data is the rest of 742. Then
So I'd like to interject here a little bit. So whenever you are training this kind of machine learning model, it is a common norm that you use 70% of your data for your training, 15% for testing, and 15% for validation. But you can change it. So try to have a decent amount of data for your test dataset. So here 1% may be good for illustration, but I would prefer at least 20% for the test size. But right now it's okay. It's just an demonstration.
Yes, absolutely, I agree. This is definitely not the best case. So since we have a very small data set here, I'm using this to get a demonstration, but of course, we will be adjusting a lot of these parameters in our real case. I will go over them later on. But now if we go over to our artificial neural network regression, so once again, we import some libraries. These are the libraries that we will be using. So I will explain each of these libraries with respect to where they are being used. So the first we develop the model. So if you remember the neural network, this is the step where we are defining how our neural network will look like. So if you remember the hidden layers, so there are 3 hidden layers here. The first one has 64 neurons. The second one has 128 neurons, and the third one has another 128 neurons. And then lastly, we have 3 neurons for the 3 output stresses. You remember the 3 output values of stress. So we have 3 neurons for the 3 output stresses. And our input dimension is 4 because percentage and the 3 strains, that's 4 input features. And the activation function, as Mahmudul has discussed, there are many activation functions. The one that we are using here is ReLU, or rectified linear activation function. So we're using ReLU for all of these steps. And this is just a summary of our model. And in this summary, we can see how many weights and biases the neural network has to optimize. As you can see, 320 for this layer, this many for this layer. In total, the neural network has to optimize 25,539 weights. So next, if we go to model.compile, here we are defining the learning rate and the loss function that our neural network will use. So the learning rate we're using as about 1e minus 4, and the loss function we're using is mean squared error. So the same one that Mahmudul showed. However, here notice the word Adam. So there are many optimizing algorithms. One of them is gradient descent that Mahmudul has already shown, but Adam is another optimizer. I'm using Adam here. There are many other optimizers. You can just find the list if you Google Keras losses. So the neural network we're using is given by Keras. So Keras losses, you will see the other optimizers. Then finally, when we fit the model, we fit it by splitting the test data set into 2 more sets. So I want to emphasize here that we initially had our data sets and we split that to 90, 99 and 1%. That was one step. But then now this 99, we are splitting that into again 99% and 1%. This 1% will be used for validation of each of these iteration steps, and the 99% will be used for training. This is to avoid overfitting the data, because sometimes neural networks the network will try too hard to predict the training data that it will fail to predict other test data for us. So that's why we're keeping some validation data. Now, of course, overfitting and underfitting are a little beyond the scope of this short course, but just know that validation split is something that we use to reduce overfitting. And then epochs is basically the iterations that Mahmudul was talking about, that it goes back and forth, and it iterates until the loss or the mean squared error is small enough. So it keeps on iterating. So it keeps on iterating and the loss keeps on decreasing. As you can see, we have used 1000 iterations here, but if we went for even more, then maybe we would get even more accurate results. And also note that there is a basically opposite relationship between the learning rate and the epoch or the iterations. Because if you give a very fast learning rate, that is a very small value, a very large value here, then the data will jump around too fast and you will be able to fit the model with small number of iterations, but it will not be very accurate. But if you give a very small learning rate, it will require a lot of iterations to go to the final result, but it will be more accurate. So these are values that we will need to tinker around to find the optimum value for our specific data set. And here we can see that there is no overfitting because the loss and the validation loss almost overlap. But you can see there is still a slight downward slope. It would have been better if we trained it for further iterations. So these are parameters that you will adjust. And finally, to check the predictions, what we do is we use our model to predict the test data set. For the test, that 1% test data, we try to predict it. And the values that we get, we give it R-square score. R-square score is basically if you we're plotting actual versus predicted data. Okay, so actual data on the x-axis and the predicted data on the y-axis, and it should be theoretically, if it's a 100% accurate model, it should be a 45-degree straight line passing through the origin. However, which will have a R-square value of 1, but you can see the R-square value is 0.75, so it's reasonably approximately accurate, but it's not exactly accurate. So these are this is the score that we will try to optimize. We will try to tinker those parameters again and again to find the best value that gives us. And then we can remember, we finally, when we predict the results, these predictions will not be our stress in megapascal, because we used a scalar. We used scaling. Remember, we used normalization. So we need to inverse that normalization to get our final results. So we use scalar y dot inverse transform to get the final predictions. And then we print those predictions here. And these are our megapascal stress values. You can save it using this command to a CSV file. We can save the model. We can save the weights and bias values. We can look at the weights and bias values like this. And finally, we can use it to try to predict a stress strain curve. But as we saw, it was only 74% R-square score. We will see that it has successfully predicted this part of the graph, but in this part, it has not successfully predicted it yet. So this is something that we need to solve using more data and using better parameters. We can change the number of neurons, learning rate, epochs, and a lot of other things. So this is how you train a neural network. Any questions?
I'm not sure how many of you actually follow along, but I think it's getting late in Bangladesh time. So if you have question, you already have this code, you can go through this code and try yourselves. If you have any question, forward it to us later on, that's fine. But if you have any question right now, please feel free to ask. So if not, I think we have some scope for discussion. Like, for example, using this technique, how you can use it for your own research. So what we are showing here is basically what we discussed earlier today. It's kind of fitting some data using some regression model, but we are using a fancy thing here, which is neural network. Now the question is, the important part is what kind of data you are working with, what kind of problem you are working with. So think about it, how you can extract some data and then fit it using a neural network. So that would be one interesting idea. So I know many of you are working with molecular dynamics simulation. So for example, if you can generate some stress strain data using molecular dynamics simulation, then you know, like there are lots of stress strain data point in your simulation data set. Now you can think of using a neural network. For example, so you cannot do simulation for many temperature. Maybe you can just do 5 temperature. Then you can think of approximating those using a neural network that can give you the intermediate temperature. And we did some work earlier in heat transfer as well. So Rabbi published one paper earlier where he tried different non-dimensional number and generated data and try to fit it. So you can think about, we just show one example using materials modeling, but it can be explored in different kind of problems. So it doesn't necessary to use it only for this kind of modeling. And one more advanced thing I would like to talk a little bit. So if you see the prediction here, you can see our prediction is not that good. So one of the way definitely is to modify different training parameter and see how it impacts the output. But from my experience, I did this quite a few time right now. And from my experience, there are some other advanced technique that you can use to have better fit. For example, say one of the current trend or current research trend is basically using uh, physics based neural network. So what that physics based neural network do, so you can see here we consider the loss function is just the difference between your original data and your I mean predicted data. But you can think of, you can actually implement the equilibrium equation, which is the fundamental mechanical equation or mechanistic equation, and then you can optimize your neural network based on that. In that case, you will integrate the physics into your neural network. It's not necessarily just some mathematical trick. It will be a physics based model in that case. Also, another important thing is there are another different class of neural network. So one important class of neural network is recurrent neural network. And in recurrent neural network, you have some long short-term memory term. So can you, Shajedul, go to one stochastic curve? So if you see the stochastic curve is a function of your applied strain, or you can think of time. So for example, your stress of this point will depend on the earlier point. Your stress on this point will depend on the earlier point. So if you can remember something or keep something, some information in your memory, then it might be better to predict that. So from my experience, I tried feed-forward neural network, I tried recurrent neural network. So if your data set have some sharp changes, for example, say maybe your data looks like this, you have a sharp change and then maybe increase again. So feed-forward neural network is very poor to capture this kind of sharp change. But if you use recurrent neural network, they can capture this kind of sharp change. And for example, if you're interested into financial engineering, for example, say stock market prediction, those are very common application of data science. So in that case, you will see many fluctuation, and those kind of thing can actually be predicted. So these are very powerful techniques. So that's what I want to convey to you, that neural network is a very powerful technique. Some people are quite skeptical about these techniques, data science techniques, but just to mention you that this is the new paradigm of science and engineering. So you should be skeptical, but think about how you can use it to interpret your data, or just use data science as a tool, not maybe the whole thing. Try to interpret your data using data science. And also another important part would be that I said earlier, that how you can integrate physics with these data science techniques, because computer science people are developing algorithm. They solve problem, for example, say cat and dog classification or natural language processing. But you are expert in the mechanical engineering and mechanical science. So you know the physics better than any computer science people here. So you need to think about how you can integrate those physics into this kind of data science technique. So neural network is just one of them. There are many other machine learning techniques that you can use. So if you can relate it somehow to the physics of the problem, or if it can give you some idea. So if you remember in our keynote talk today, so we saw like it can be fitted with a cubic polynomial, but machine learning can tell you a little bit more, like what other functional form that it can fit. For example, so if you use symbolic regression, that can give you more form of equation, not just picking, I mean, trial and error. It will give you the form of the equation. So that would be my suggestion. Use data science as a tool, learn about it, try to keep it as a part of your projects. That will give you better credibility in terms of every aspects of your future career. So that would be my conclusion. If you have question, feel free to ask. I think there are some question in the chat box. Yes, I think I already answered this question, right? So if you have any sharp transition,
From my experience, I'm talking from my experience that this kind of feed-forward neural network will not do. And there are another class of neural network, very important type, which is convolutional neural network, right? There are different types, but if you're working with image-based something or some signal, then probably convolutional neural network is the way to go. So it depends on the type of problem. You cannot just say, okay, I just learned this one and I'll apply this one in everything. It will not work. But there are very strong mathematical background behind this neural network stuff. So I mentioned something earlier that there is a universal approximation theory, and people have already proved it mathematically that any mathematical function can be approximated using the neural network. So it is based on how many layers you choose. It's based on what kind of activation function you choose. So it's possible to approximate any kind of function. Even you can do finite element using neural network. That's what we are developing in our group. Even shape function and everything can be developed using neural network. And another question I can see is polygon structure. So you need to identify. So for example, if you want to train a neural network, you need to identify what are your input parameters and what are your output parameters. And what you want to learn is basically the functional form between this input and output, right? So from your problem, maybe just I'm guessing it. So if you're working with polygon structure, you can think of grain size or grain diameter as one input variable, and maybe what else? I don't know, if your work depends on the temperature, you can think of that. And also for stochastic, you can change the size of your RV that you are considering for modeling your grain structure. So those are the things you can vary and see the effect. I mean, output can be stress and response or whatever you want to. I'm not sure if it answered your question completely. Okay. All right. So if there is no more question, I would like to thank you guys again to attend this short course part. Feel free to forward me any of your question later on.